students. Today we are going to discuss in this lecture generalization, okay, as part of the system modeling topic that we have been discussing. Generalization is basically whenever we have some classes which have some commonalities. Suppose there are few classes which have some common characteristics. Then what happens is that we normally create tends to create a separate class with those common characteristics, and from there the specific classes tends to inherit. This is a very common practice that we adopt in different fields of our life. Okay, so these different classes which derives from that common class or the general class basically adds some specific characteristics to those common characteristics which it has inherited. Okay, suppose we can have some common uh, some generalized classes like animals, cars, houses, etc. So if we have animals as a generalized class, then obviously the different categories of animals will have the same characteristics as derived from the animal class. So same applies to the other classes. So this kind of like suppose for example, as you see here, this one example, squirrels and the rats are rodents. So rodents is the generalized class. It's a generalization from where the squirrels class and the rats class derive some properties of the rodents. Okay, and adds to it some specific characteristics of its specific classes. Okay, in object-oriented programming, it is normally it is a common practice to look for the scope for generalization in a program. That is, for those classes, if there is a common class that can be created from which the um, classes can derive. Okay, so this is mainly useful. Suppose if some changes have to be done, then instead of looking for every specific classes to make the changes, the common attribute from which the generalization has been done, that can be changed in the generalized class. So it makes the changes easier in the program. Okay, so in the object-oriented programming like Java, generalization is implemented using the inheritance mechanism. Okay, that is built into the mechanism, built into the language. Okay, so in generalization, what happens? The attributes and operations that are associated with the higher level classes uh, actually are also associated with the lower level classes. Only thing is that the lower level classes, in it apart from using those attributes and the operations which it has inherited from the upper class, super class, it adds to each some specific attributes and operations. That is it adds some specific attributes and operations apart from the operations and the attributes it inherits from the super class. That is what in the generalization the lower level or the subclasses do. Okay. So here is the generalization hierarchy, which is shown the generalization as the generalization here. That is, the doctor is the supermost class from which the hospital doctor and the general practitioner derive some attributes. So these are the subclasses which derives attributes from the doctor classes. Similarly, there can be consultant doctor or team doctor in the hospital. So now these two classes become the generalized class from which the attributes are derived by the consultant and the team doctors, and it adds specific attributes of its own to each specific classes. Similarly, the team doctor can be either trainee doctor or qualified doctor. So some attributes which are applied to the trainee doctor are part of this particular class, the specific class, and it derives the attribute from the team doctor, which is a generalized class for the trainee doctor as well as the qualified doctor. Okay. So this way the generalization can be stated. In the previous diagram, it was only the class name which was stated. Now, in the generalization format, basically you can specify the detail of the classes, like the attributes which are specified and the operations which are there. Suppose for the doctor class, the attributes are the name, phone, and the email, and the operations are the registered and the deregistered. So these are the two operations for which it interacts with the subclasses. Okay. Similarly, hospital doctor and general practitioner also have some attributes and the operations. So of its own. So the attributes, it is not mandatory that it must have operations. So suppose these two um, classes have some specific attributes only. Then these two attributes, suppose these are the attributes which are specified here, actually are the specific to these classes. Apart from the generalization, the classes in the hierarchy can have another type of relationship which is called as the aggregation model. Okay, aggregation model is basically the part of relationship. It is called as the part of relationship. Why? Because the subclasses are considered to be the components of the upper class. That is the one class is considered to be composed of some other objects, or some one object is considered to be composed of other objects. So the one of the composite object is the whole object. We can call it the and as the whole object, and the it composed of the other objects which can be considered as the parts of the previous object. So basically, aggregation model shows how the classes are collections of uh, or composed of the other classes. Okay, so this is what the aggregation model means. So here is a diagram which shows the aggregation model for a class patient record, uh, which can be considered to be composed of the patient and consultation. So a patient record can consist of one patient detail, that is why it is 1 to 1, and number of consultations. So these are part of relationships. They are not deriving anything from the upper class, the um, uh, super class, but it is a part of relationship. That is, this particular class is composed of a one patient and number of consultation classes. Okay, so this is called as the aggregation association. When we have to represent the dynamic behavior of the system, then when we have to view the dynamic behavior of the system, then we normally use the behavioral model. Okay. So this you can say as the view of the system while it is executing. Okay, so it basically represents what happens to the system, that responds to a particular stimulus from the environment. So when there is some kind of stimulus from the environment that changes the behavior of the system, or suppose the system responds to that stimulus and does something, and whatever it does that is in response to that stimulus is the behavior of that particular model at that point of time. So this is captured in the behavioral model. So there can be two kind of stimuli that can actually affect the system depending on the type of the system that is being used or that is being developed. So there are certain kind of stimuli can be a data or an event. Data stimuli means when a data is arrived and data it is you can say when the data is taken as the input, and in response to the data taken as the input by the system, it does some operations and produces some output. So this is called as the data that is the data driven behavioral model. Okay, where data is used as a stimuli. Similarly, events can also be considered to be a stimuli when actually events triggers the system processing. That is, due to some events the system does certain things which you can say it does some processing, so then it is called as the event driven. Okay, so uh, events can also be associated with the data, but normally we'll just consider as the separate parts here to for better understanding. That is, either a stimuli can be a data or a stimuli can be an event. Data driven modeling are basically that uses the data as the input to do some processing for the system and then produces some data as the output. Okay, so in the analysis part in the year 1978, the data flow diagram was is actually developed. In the data flow diagram, basically it is the data flows in the system with the functions, different functions processing the data. It basically shows the inputs of the input of the data to the functions. Okay, but in the UML diagram, there is actually functions are not independently used. So DFD, the data flow diagram, is not basically is not what used in the UML diagram. So for UML diagram, this data processing part in a data driven, that is the systems modeling, is shown using the activity diagram, okay, or is also shown by sequence diagram, by both, either of these two diagrams, because in the UML diagram we consider the processing to be done by, is accepted or is done by some objects, okay. So instead of taking the independent functions there, so that way it is different from the DFD, data flow diagram, but otherwise DFD also represents the data processing task. Now data processing sequence. Now here uh, mostly this one, data driving modeling with the activity diagram or the sequence diagram, is actually used during the analysis of the requirements, okay. That actually is used to show the end-to-end processing in a system, the way data is processed within the system. So system accepts some data as the input and does some sequence of processing inside it, and then produce the output data as the output, okay. So that is what the system do from the end-to-end processing of the data. So here is the activity model for the insulin pump operation. That is the blood sugar sensor is the activity. Okay, is uh, basically blood sugar sensor is the object that gives data to the get sensor value. Okay, so get sensor value uh, produces some output, and it basically uh, those output is considered to be the sensor data, which goes to the compute sugar level, okay. Then blood sugar level is the output of here, the compute sugar level, which goes to the calculated insulin level. That way the insulin pump gets the signal of what is the exact amount of insulin that is to be provided to the patient. So this shows the sequence of the activities and the data that is being processed from one activity to the other, okay. So activities here are the get sensor value, compute sugar level, calculate insulin delivery, calculate pump commands, okay, and the control pump, and these are different data that are flowing inside it, okay. So in the order processing can be a sequence diagram. Suppose, for example, the order processing sequence diagram. This also shows the data driven modeling here, because the order is being processed. Suppose from one active one there are this is one actor, the purchase officer, and there is another actor which is the supplier. So it is basically the way the order form is being filled up, and that actually the filling of the form, then validating the form, then if validation of okay, then it goes to the object, that is the data budget, okay. From budget it goes to the data store order, okay. From then it sends, and then the supplier basically gets the order being processed, okay. So this is what the order processing flow and sequence diagram that represents the sequence from one end to the other end, and it indicates the flow of data from the one end to the another end, and the data being processed in this sequence. So this is a data driving model using the sequence diagram. Event driven models are the modeling where stimuli is an event, okay, that does the um, system to do the processing, okay. So when a event acts as a stimuli instead of the data for the system to do certain processing, that is called as the event driven modeling. Suppose for example, a land phone switching system responds to an event such as receiver off hook, okay, um, by generating a dial tone. So if a uh, line phone switching system responds, that is the switching system responds to an event, that is the receiver off hook. So when the receiver lifts that particular phone, okay, so it actually dial tone starts generating. So this receiver off hook is a event which actually changes the state of the system to the land phone switching, that is the switching system response to this particular event, okay. Similarly, there can be other events like, valve open, valve close, uh, that is some system controlling a valve may move from one state to another because of the valve open state. That is, the stimuli is the valve open. When the valve is open, it moves from one state to another state. Similarly, valve closed means it again moves to another state. Suppose when the stimuli is received. So this way, when the event causes the acts as a stimuli for the system to respond or system to process, then it is a event-driven modeling. The event-driven modeling is often shown using the state machine models. That is actually we can call as the state charts. Okay, that is you can say different because the system moves from one state to another state because of some events. So we can call this state machine models as the state charts. So when we have such this in this particular model, the state machine that is system states are shown as the nodes, and the events are shown as the arcs between these nodes. Okay, so we'll see with some example in the next slide how the state machine models are used or drawn. So here is a state diagram of a microwave oven that shows how a system moves from one state to the another state because of some events. So here is the starting point, and when the microwave oven is considered to be in the waiting state, that is the this particular state is called the waiting state. During the waiting state, it keeps on displaying the time. Okay, so there may be these are the events now that may occur to this waiting state. Either it can move to the full power because the full power is given, or a half power is given. If the full power is given, then the state of the machine goes from waiting to the full power. Okay, and it actually sets the power to minus this 600. Similarly, half power is given means it sets the power, it goes to the state half power, which actually do the setting of the power to 300. Okay, and these two states can go can keep on switching between these two states from one to another by using the if in the full power, if you give half power again, it will move to the half power. In the half power state, if you give the full power, it will go to the full power state. Okay, now during this states, if you set the timer, then it goes to the state, the system goes to the state set time. Okay, so what in the set time, actually it gets a number to set the time. Okay, so when you give a number, it remains in the set time state, but the number being included here. Now there are two events that may occur, that is this arrow indicates the events here, the door open, door close. If you use the event door open, it will go to the disable state. Okay, similarly if you then again close the door, it goes to the enable state. And similarly from the set time state, if your door is closed, it goes to the enable state. From the enable state, with the event start, if you press the start button, it goes to the operation state. So it operates the event. Okay, operates the oven. So it goes to the operation state. In the operation state, if you basically uh, open the door, it goes to the disable state where the it display waiting is displayed, and it goes to the disable state. Okay, and then finally, once this time is over, it goes to the waiting state where it displays the time. So those uh, events, these states, actually state of the machine, are these are the different states of the machine: waiting, half power, full power, set time, disable, okay, enable, and the operations. And these are the corresponding description for these states. Waiting means the oven is waiting for input. The display shows the current time. Okay, that is, you can see in the previous diagram, the waiting, it is in the waiting state with the display in the current time. So this is the waiting state. Similarly, half power means the oven power is set to 300 and the display shows half power. Similarly, full power means the description is here. The oven power is set to 600. The display shows full power. That is the set time is another state of the machine where the cooking time is set to the user's input value, and the display shows the cooking time selected and is updated as the time is So disable means the oven operation is displayed for safety. Okay, is disabled for safety. So interior oven light is on, display shows not ready. Okay, so this is what the disable state means. Similarly, enable state means the oven operation is enabled, interior oven light is off, display shows ready to cook. Operation means the oven is in operation, interior oven light is on, the display shows the timer countdown. So countdown is shown in the display. On completion of cooking, the buzzer is sounded for 5 seconds. Oven light is on, display shows cooking complete while buzzer is sounding. So these are the descriptions for different states to which a oven can move in the state diagram. Similarly, these are the events which causes for those states which have been shown in the previous slide, those states to change from one to the other. Okay, because of these events. So description of the events are shown here on the right hand side. That is, the half power means the user has pressed the half power button. Full power means the user has pressed the full power button. Timer, the user has uh, pressed one of the timer button. Number is means the user has pressed a numeric key. Okay. Door open means the oven door is switched. Oven door switch is not closed. So door close means the oven door switch is closed. Start means the user has pressed the start button. Cancel means the user has pressed the cancel button. So these are different events which causes those uh, states of the machine which has been system which has been shown in the previous slide to move from one state to the another state of the machine. Similarly, there is another example where microwave oven operation. So for the oven operation, that is the microwave operation, now is the oven operation. Here it is the same kind of operation. These are the different states: the checking, cook, alarm, and done. Okay, disabled and waiting. So here uh, you can see this, checking state. It goes to the it so displays the check status. Okay, and with the event this turntable fault, it goes to the alarm state. Similarly, in the alarm state, it is with this checking state, with the emitter fault, it goes to the alarm state. Similarly, if it is the event is okay, then it goes to the cook state from the checking state, and the uh, with the timer, timer being set, it goes to the cooking state and does the cooking. When the timeout, it goes to the buzzer for 5 seconds. Okay, and from there it goes to the waiting. Okay, so this is what the state diagram for the microwave oven operation is shown. So key points that we have discussed in this particular uh, lecture is that the behavioral model actually are used to describe the dynamic behavior of the system while the system is in execution. Okay, this behavior can be modeled from the perspective of data processed by the system or by the events that stimulate responses from a system. So the stimuli can be either data or an event. Okay, if data is the stimuli, then it basically processes the data with some input data being given to the system that goes through different uh, system module or system activities, and then the output data is generated through this particular uh, sequence of processing that is being done to the data. Similarly, when the event is used, the system can move from one state to the another state. Finally, some response is being generated. That means which indicates the completion of the process. So, activity diagram may be used to model the processing of data. So, one of the way to represent the processing of data is the activity model, as we have shown with an example in the previous slide. So, another is the sequence diagram that can also be used. State diagrams are used to model the system behavior in response to the internal or external events. Okay, so state diagram we have just shown in the last two slides, where the state diagrams are used to represent the different events which causes the change of state of the machine. Okay, thank you.